Today we're going to have two guest speakers. We're going to have Dr. Fazil Khan from MME and then Dr. Kathy Almquist from CPE, and that's Mechanical and Manufacturing Engineering and then Chemical and Paper Engineering.
Good morning, everybody. Slightly different setting for me. I'm usually getting a little nervous when the materials class I teach has population exceeding 60. So this is a rather large gathering, so I think I'll be able to adjust. Anyways, my name is Fazil Khan. I've been with the department since 2003. And I'm guessing the objective here is to kind of give you a little bit more exposure to different areas of research going on within the department and things you may be wanting to later on become involved in. And what I tried to do over here is give you a little bit or put together a presentation that exposes you to some of the key areas of material science. And then, of course, I couldn't pass up the opportunity to include a little bit more detailed perspective on what I do in the area of research. And it's always involved undergraduate and graduate students, so it's definitely a viable area of research. And also, just to let you know, it's good to be aware of the different areas of research going on and consider that as a possibility during your academic stay here, whether it be during the summer or during the course of the semesters. In one area of research or another, if you don't like the first that you were involved in, you can always change. I was a very late entrant to mechanical engineering. Whole of undergraduate and graduate school was in physics, and then I later on went into engineering and work in the area of polymers. So in the general field of materials, please, general class policy of mine and with presentations as well. I'll definitely open or be receptive to questions at the end, but also during the course of the presentation, if you've got some question pertaining to a slide or anything that I have up over here, don't have any reservations about raising your hand, and I'll be happy to answer whatever question comes up. Okay, so when we're talking about the field of material science, you might be thinking, some of the newer materials that come into sort of the attention of in technical publications, or manufacturers are touting things made out of carbon fiber, whether it just be for aesthetic reasons. The carbon fiber panel you'll see on a Toyota Corolla's dashboard, well, that's not really functional. It's more of a veneer for aesthetic reasons than anything else, but there's functional applications of it as well. So what I wanted to show you over here was sort of over the timeline here of the world, going back from way back when. A lot of the materials we use have been around for a long, long time. A lot of like the titanium alloys and stuff, these super alloys, some over here, they've been around since the 1940s and 50s. In fact, a lot of the aviation industry back in the 60s, a lot of the new Russian jets coming out in the 60s, the whole Cold War spurred research and industrialization, had a lot to do with the development of these newer higher temperature alloys. And the plastics. You might think, well, plastics seem to be sort of coming up later and later. You look at more and more products in which polymers, plastics, are starting to supplant metals. You might think that's a recent trend. Well, yeah, that's gotten more and more prominent over the past few years because polymers have become more and more high performance over the years with more tailored specialized properties, but they've been around for a long, long time. A lot of these materials like acrylics, so a lot of times when you have glass windows in a greenhouse or something like that, it's this acrylic material. The material down over here, polycarbonate, if you wear glasses, typically the material is polycarbonate. Headlight covers on automobiles, they're all polycarbonate now, unless it's a relic from the 50s or something, which is still using glass. A lot of it is now polycarbonate. The materials that we use now have been around a long time. And these are the composites, like carbon fiber. It's been around since the mid-'80s or so in structural form. So they've been around for a while, but that's not to say that they're not still the subject of intense research. Steels, for example, right up over here. Yeah, industrial age, been around or led to the development of a lot of bridges and stuff. You go to New York City, you see a lot of some of the older the bridges and stuff, and in other places as well. Well, they're attributed to steel, but there's still a lot of research going on how steels can be made better for automotive use and in other applications. So when we're talking about the field of material science and the way I like to introduce it in my coursework, am I blocking your view from too far forward? Okay. So in the field of material science, what are we looking to investigate, or what is it about materials that interests us? Well, we're looking to improve their mechanical properties. We want to make the electrical conductivity better, so we have less heat losses in electronic devices. If you think over the years, the time on your electronic devices becomes longer and longer. Well, maybe not, because they have more and more functions and you're using them a lot more, sometimes when you shouldn't be. But essentially, the longer battery life is sometimes due to lesser resistance in the material, better electrical properties. So we're trying to improve the metals or the materials that we already have. At the same time, we're looking to develop newer materials for different newer emerging applications. So those are entirely new chemistries for polymers or newer alloys that may be developed. And it's not just the big industrial giants. Sometimes, for instance, late 1990s, bicycle manufacturer Klein developed their own aluminum alloy specifically for bicycle applications. Later on, the patent was bought out by other companies, but you can have lots of even small manufacturers working in this area. It becomes expensive for smaller manufacturers, but still, they can do a very good job at it. And so in addition to this, one of the key areas we try to, I try to bring in the courses that I teach, the two materials courses, is also how do we investigate the mechanical properties? So you have different materials and you want to say, well, one is stronger than the other. How do you go about finding those properties? So for example, the nylon used in parachutes, I got to experience that quite recently. Rather reassuring, the polymers are of the strength and durability that you need them to be, but it's a very, very lightweight fabric, the nylon, the amides that get used over here. So it's about the development of new materials. That is a specialized mountain bike frame, and also about the failure. So when we're talking about the mechanical properties of materials, it's also dealing with how materials fail. So there's that kind of like the forensic analysis part of mechanical properties also comes into play. So in the first part, for example, so we begin by understanding, so if you want to manipulate the properties of materials, you want to make them better, you want to make your steel stronger. Like if you're looking at this picture over here, this is a saw cutting through an I-beam. Well, what's the saw blade made out of? Steel. And what is it cutting through? A steel beam. That's an I-beam, which you'll probably not be able to see with all the tiles over here, but the building has a large amount of these I-beams for support. So clearly, the properties of one steel are very, very different from those of another. And understanding the structure of that steel at the atomic level, what have we done to that iron structure? How much carbon have we added to it? What phase or what structure is it in is all part of material science. And so if you want to alter the properties, so let's say you have a certain piece of aluminum, you want to change its properties, you've got different ways in which you can do that. You can change its composition. So sometimes if you say steel's not pure iron. It has carbon and maybe 5 or 6 other, at least, other materials added to it. Vanadium, chromium, for example, all of those might go in it. Has anybody heard the term chromoly? If you're a bicycle enthusiast, the manufacturer will say it's a chromoly frame. Thank you. And that chromoly basically means it's chromium molybdenum added to the steel, making it much stronger than ordinary steel. So you can have plain steel, which just has carbon, then you can add a little bit more of chromium. I'm sure you've heard of the elements or metals before, and you can improve the properties by almost like a factor of 2 or 3, or even more. You can just basically change the heat treatments. So a lot of times here, for instance, in this aluminum example that I'm showing, this is how aluminum foil is made. I'm sure you've used foil relatively recently. It starts out in big slabs, sometimes up to 12 inches thick, and it gets put between these rollers, and you reduce the diameter to maybe a couple of inches, and you continue this process over and over until you end up with aluminum foil. So imagine having a slab 12 inches thick, which you have successively rolled down into aluminum foil. And all the properties of this aluminum along the way are treated with heat treatment. So it's not like you melt the aluminum down and say, okay, I'm going to try to improve the properties. It's heat treatments that allow you to do this. So again, in the case of metals, you can really improve the properties by several orders of magnitude simply by, well, maybe that's an exaggeration, maybe like by a factor of 4 or 5, simply by applying heat treatments. And you can also, if you manipulate something mechanically, so if you were to take a small, let's say ordinary paper clip you might have available, if you bend it 2 or 3 times, it's actually gotten stronger after those few cycles of deformation that you've done than it originally was. And that actually is also used in the manufacturing sector to ensure that parts have a certain strength. So when you start out with these rolls of sheet metal and you stamp this body part from it, so this is like the complete side of a vehicle, because of all that deformation that's gone into this piece of sheet metal, it's actually become stronger because of it. So even if you discount the heat treatment, you do not go in and add anything else to the metal, simply the fact that you've deformed it has made it stronger. So all of those you have to be able to quantify, say, how can I predict how the material is going to change? Okay. So just wanted to give you an idea of like different materials. So for example, aluminum, it's used in a very, very large quantity, and it goes into transport. I'm sure you're familiar with beverage cans, a lot in construction, appliances and stuff. And it can also be used in a very different application, non-structural. For instance, the solid rocket boosters over here, previous ones used to be liquid-based. They're not really very stable or easy to store. So solid boosters typically use a lot of aluminum powder. Also, just one more area I wanted to talk about before I move into my area of research, composite panels, like fiberglass I was mentioning. I particularly wanted to bring this in since it gets advertised more and more in new products. It's basically a carbon-based fabric, and then you sandwich it in layers using an epoxy. So it's basically a multi-layer composite. It has a lot of strength. It's very, very strong, very rigid, and you can make it to whatever shape you like. So a complete bicycle frame can be made in a continuous form. So it's not you're assembling different pieces of it together. Again, automobile parts. So this is a structural application for carbon fiber. So you've got a roof panel being made. So you see she's cutting the sheets here, and then it's going to get put in an oven. And complete front frame of a vehicle made out of carbon fiber. And you can see how complex geometries can be easily included in. Now, I'd be pleasantly surprised if anybody can tell me which vehicle that is. No? Okay, the limited production Aston Martin 177 goes for a little over $1 million. And of course, you might have heard the Boeing Dreamliner, a little bit behind schedule, meaning a little over 2 years, but that's okay. It'll be a triumph of engineering when it flies. You've got large sections of the fuselage now being made out of carbon fiber. So composites very much being used on a much larger scale than they have ever been used in the aerospace industry before. You've got much larger windows in the airplane, and you have a much higher humidity level in the airplane, all on account of the fact that you're using structural composites, and much higher internal pressure too, so your ears really don't pop as much on during flight. Here's the area I'm interested in terms of polymer materials. This is the knee joint, and you've got the femur up at the top, tibula at the bottom, and every time you're moving, they're rotating, or the femur is moving relative to the tibia, and you've got the meniscus over here in the middle. It's a cartilage point. I'm sure you've heard of meniscal tears before. Unfortunate, or hoping it's not in context to an injury you might have sustained. And a lot of repairs are being done now to biological injuries using polymers. For instance, something simple as like a hernia operation will use polymer meshing so that it can be replaced. But I'm focusing more on components like the knee and the hip joint and the polymers they use. And so what happens typically if there's, for instance, if there's arthritis or there's some other autoimmune disease and the cartilage here becomes degraded over time, or if there's fracture there, you basically have bone-on-bone contact between the femur and the tibula, and that creates a lot of pain. And so what we have for that are biomedical implants. One of the first knee implants or hip implants was done all the way in the late 1950s using Teflon. I'm sure you've heard of the materials, like the non-stick coating on your frying pans. That's Teflon. And they chose it because they thought, wow, it's a very slick polymer, very low friction. It should do very well in that joint. But the problem with that was, and it was discovered within the first 1 or 2 years, it wears out at an extremely fast rate. So that cartilage replacement piece that you put into the joint, well, it starts to degrade or starts to break up very quickly. And once you wear something out, what are you producing? Debris particles. So imagine taking like a piece of plastic and running it on sandpaper, you're producing a lot of that powder. Well, that's inside the body now. That causes a lot of problems. And so we want a material that does not wear very, very quickly. So these are some of the older geometries. You can see kind of like a pin joint, which allowed for very, very little rotational movement. Now, the knee joint is extremely complex. It's kind of like a hinge joint, but it also allows a lot of like azimuthal rotation, which some of these earlier joints didn't allow. And this is the current generation of the knee joint, and I can show you that over here. So this is the bottom piece that you're seeing here. This gets inserted into the femur. This is the polymer piece, or the polymer material, that I do research on. This is made by DePuy Orthopedics up in Warsaw, Indiana, one of the top 3 manufacturers in the world. And this gets attached to the femur up at the top. So this is the tibial implant. This is the femoral implant. And so then they allow you rotation or movement like this. And if you imagine the number of cycles involved in day-to-day life, the main concern is this going to hold up over the course of the patient's life? So how long are we expecting these implants to last? Ideally, it would be the life of the patient, but typically they go for 8 to 10 years. And you're noticing here what I was mentioning in some of the earlier implants, it's been completely worn out. And the problem with this degradation is that those particles get embedded in the bone around the implant, and they cause the necrosis of the bone, and the implant becomes loose, and then you have to have revision surgery, which is very bad, because you have to go pull the old implant out and then put a newer, larger one in. So that's something to be avoided. And so there's continuous research in how to improve the quality of the materials. We've just tested a brand new materials, just got an FDA approval, and it shows much better wear resistance and strength compared to the existing line of materials. So that's some research that's going on here in the lab, and it's been done by my graduate student and one undergraduate. Yep.
How do you test these? Because obviously if something's wrong with it, putting it in case or something you need is a good idea.
Well, initially, there's several different ways. We test the properties of the polymer, like, for instance, what I do in the lab, and we try to figure out how the polymer is going to respond when you put different loads on it. And then, for instance, like shown over here, we use computer modeling methods to predict how it's going to deform over the course of the service life of the part. And then secondly, prototyping. This is done towards the end of this whole process because it's the most time-consuming, most expensive. You take one of these joints and you have an actual knee simulator. It's a large machine which simulates the walking motion and then introduces maybe if you were to jump off something, run, meaning sudden loads in the whole process. And you let that machine run for a couple of million cycles, simulating 7 or 8 years of use. So you'll have one of those tests running for 6 months to a year, nonstop in some basement in the test building. So a lot of rigorous testing going on. And I'll leave off here. There's some additional materials as well. Let me just make a quick reference since I have it. There's some materials that can change shape when you trigger them. So for instance, you had this metal wire. You could straighten it out. And if you apply heat, it'll go back to its original shape. I have some samples in my office if you're curious about these materials. I could show them to you. But where are these materials used in biomedical application? For example, in stents. If you have to open up a blocked vessel, you have a stent that's been collapsed. You insert the sort of mesh made out of this material, and as soon as you trigger it, just like you saw over here, it'll go back into the expanded geometry, and it can be used to open up clogged blood vessels. So those are also used in biomedical applications. 2 minutes, I just wanted to mention, as I said, it's also about sort of like the forensic side of materials. And a lot of the research on why we've had aviation disasters is related to material science. There are new materials being developed. A lot of the piping for underground waterways, passage under the bridges. These are made out of soy products. You've got railroad ties over here. These are made out of recycled plastic, for instance, polyethylene and nylon. So these are all plastic supporting the weight of the railroad. Coconut husk being used in the application shown over here. These are seat cushions. And no, it's not the final resort of a manufacturer like Hyundai to use these. These are actually used in Mercedes-Benz products. So a lot of reuse of material. And so just to try to cover a bunch of different areas. Any questions? All right. Thank you.
Ready? Well, my name is Kathy Almquist. I'm in the Chemical and Paper Engineering Department. And Mr. Setlock asked me to give a presentation to EAS 101 students. You guys aren't 30 students, you're like 400. So I too have a fear of public speaking, but I'll do my best. So I'll talk to you today about some research opportunities, samples of projects that are in our department, and some selected projects that I've worked on with students. You guys have heard of FIRE, F-Y-R-E, First Year Research Experience. This is an opportunity for freshmen to get involved in research early on. I've dealt a lot with undergraduate summer scholars. This is typically after your sophomore or junior year. If you want a research experience, it's a 10-week opportunity. You get a stipend, you get 12 credit hours. You get some research money for materials and stuff. It's a decent program. You'll have to work with a faculty mentor for 10 weeks, and they expect you to work 40 hours a week in a lab. Independent studies, these can be done at any time. For credit, without credit, you just need to ask a faculty member to sponsor your research if you have a project idea, or if a faculty is in research and you want to work with them, I encourage you to go talk with them. And finally, the senior design and capstone experiences are an excellent opportunity to, it's like your final hurrah at Miami, where you get to do an open-ended project and used all your education that you've received at Miami to complete a project. So I won't go through all of these, but these are the students that have worked with me. And what you'll see is that I do have a history of working with undergraduate students, anywhere from transport of fatal particles through sand. What this is geared towards is that when water is treated, drinking water, it's filtered through sand beds. And if somebody wanted to put, say, a nanoparticle in your water system, will it make it through the sand bed? And that was a question that we wanted to ask, is the transport and fate of these manufactured nanoparticles and whether they'll get into our water and drinking water systems. I do a lot with catalysis, so the rest of these are in catalysis, both thermal catalysis and photocatalysis. By the way, what does a catalyst do? Speeds up the reaction. So whereas Dr. Khan talked about materials from polymers and metals and alloys, we also work with materials in metal oxides, and paper is a polymer. So this is another example of independent studies that I've worked with students on. Again, I'm just showing you these as a history that we do work with students on a consistent basis. Senior design capstones. Again, this is my experience with students, but we've worked with, last year I had 2 teams. One was catalytic gasification of coffee, and the other was anaerobic digestion of horse manure. Miami has 50 horses. They currently stockpile or landfill their manure. It's not a very good use of it, and horses generate like 50 pounds a day per horse. So it's not trivial when Miami has 50 horses. Catalytic gasification. This is in the renewable energy realm. if we could take waste products and make syngas, which is carbon monoxide and hydrogen, we can then recombine CO and H2 to form any liquid fuel. So it's an effort to take waste and make it into valuable products. This here was the start of our gasification research with students, and that was part of the Miami University Interdisciplinary Technology Development Challenge, UTEC. And my team was the winner of that challenge, and I think we got $5,000 among the team. So that was exciting for the team and exciting for me. I get a plaque, they get money. And again, this shows some of the breadth of the research that I personally have worked on. But let's look at other people in our department. The professors, Drs. Keller and Coffin, are our paper science professors. You know, paper is a material. It's a polymer. And paper has lots of properties, and it comes from a very renewable resource. What? Trees. So, and you think, well, you know, paper is, what's so big about paper? Well, imagine how often you use paper, from your towels to your tissues, toilet paper, your wrapping paper, your writing paper, all your books. And not only that, they're in construction materials like ceiling tiles and wallboards, and they're in roofing. So paper is a very important material, commodity. And Drs. Keller and Coffin are internationally known for their research in paper physics, which is, as Dr. Kahn was saying, the treatment of metals and polymers dictate their final properties. That's the same thing with paper and also with the metal oxides that I work with. The heat treatment and the way you manufacture it has a lot to do with the final properties of that material. Dr. Kerr is doing an excellent job in photovoltaics. She has, she's studying dye-sensitized solar panels as well as the more traditional solar panels with silicon-based. But she's the first to put a solar active material on a piece of paper. And that was exciting. So her senior design project this year is to try to coat paper with solar active material to make a very inexpensive solar panel. If you can imagine the social, help me out with a word, implications, very good, thank you. The social implications of having paper-based solar panels. And the reason why we don't use solar panels very much now is they're expensive, more expensive than coal-fired power plants for energy. So she's working there. Biomaterials, Dr. Yousefi and our new professor, Dr. Justin Saul, they are biomaterials guys, whereas Dr. Kahn is also working on biomaterials, the polymers. These guys are also working on biomaterials. Dr. Yousefi is looking at cartilage replacements. If anyone's had a replacement in their knee or shoulder or something, you want a material that mimics cartilage. And so her research is on that. Dr. Saul is new, and my memory is lapsing, so forgive me. But he's also working in biomechanics and biomaterials for various applications. Our chair is Dr. Lalvani. He's in electrochemistry and also corrosion, which is also electrochemistry. He's done electrochemical research on, say, getting rid of trans fats out of oils. It's pretty exciting stuff. Dr. Thrash is another professor in our department. He's also a bio guy. He works on adsorption of proteins or separation of proteins. He also works in biofuels area, like making bioethanol out of switchgrass or other biomass materials. He works in fermentation. I have started a few years back trying to go into the biofuels area. I think it's exciting. I think energy is one of our up-and-coming important areas that the new engineers will have a huge impact on. As you know, you may or may not know, but some people have predicted that our peak oil has already passed, which is production is, let me go back, but anyway, oil's going to get much more expensive as it becomes harder and harder to reach, meaning our ways of mining, not mining, but drilling for oil are going to get more expensive as it's getting harder and harder to reach. We had that Gulf oil spill. The problem with that, it was a mile under water. And so it was very difficult for them to fix it once something went awry. And again, my main focus is catalysis. But I did an adsorption project recently. When I approach a research project, I think practically. Like when I worked at Battelle for a while, their motto is putting technology to work. And I really feel like that's what engineers do. We put technology to work. How do we apply our resources? How do we apply our technology to take resources from our earth and make value-added products? So obviously I need a motivation. Why would I want to adsorb mercury on de-inked paper sludge? Well, where's mercury coming from? In our atmosphere, where is mercury? What's the highest source of anthropogenic mercury emissions? It's coming from our coal-fired power plants. 80% of our energy in the U.S. comes from coal. And over 50% of the mercury emissions in our environment comes from burning coal. So the EPA just came up with this clean air regulation that they're going to try to limit mercury emissions from coal-fired power plants. That means that these coal-fired power plants are going to have to come up with some technology to get rid of the mercury out of flue gas. And it's going to cost money. It's going to cost you guys money. It's going to cost me money because that technology is going to cost the power plants money to get rid of the mercury. So one of the opportunities that they see is, well, maybe we can inject activated carbon into the flue gas, capture the mercury, and then capture the activated carbon and treat it. Well, right now, the activated carbon that they're using in some pilot scale studies is rather expensive. So here we have a waste product, sludge from a de-inked paper mill. Can we make activated carbon out of it? Because it's a waste, it should be cheaper than the other carbons. And can it absorb mercury vapors? So again, the motivation was environmental and economical. And there's also utility needs. The utilities have to get rid of mercury out of their flue gas. So any good research project starts with a literature review, and do not underestimate the value of your libraries. Whether you do the library search online or in a library, the literature review, whenever you approach a project, it should always start with a good literature review. It'll save you so much time in the long run. Characterization, we have to characterize our sludge before and after the synthesis of the adsorbents. And the way we make these adsorbents from sludge is we pyrolyze it. Pyrolysis is a process where you heat something up to high temperatures in the absence of oxygen. If there was oxygen, what would happen to the sludge? It would just burn. Then I'd be left with the metal oxides and ash. But I wanted the carbon. So then we have to characterize the resulting carbons. Then we have to characterize its adsorption performance. And no research is valuable unless you can document it and talk about it, right? So documentation is very important. So the raw DPS, the inked paper sludge, was pyrolyzed at 3 different temperatures, and we wanted to assess the effect of heat treatments on the inked paper sludge. And In adsorption, one of the key things that you want is a high surface area. So this is raw paper sludge. It's a surface area in meters squared per gram. And as you pyrolyze it, we can get up to about 50 meters squared per gram. And then there's a commercial carbon that you'd probably find in your Brita filters. But it's from Calgon carbon, and it's about 1,100 meters squared per gram. So it's really, really porous. But when you look at the pore size distribution, this light colored here is the BPL. Almost all of the BPL's pores are less than 6 nanometers, whereas for the DPS, most of them are between 20 and 80 nanometers. These are scanning electron microscopy images of the DPS. This is raw DPS. You can see the paper fibers, and the rest is just like fillers that's in paper. If you make paper, you'll know that you add calcium carbonate or clay. The clay makes it more opaque so that when you write on it, you don't see through it. And the titanium dioxide in it makes it white. So there are fillers. There's also materials in it, in the paper, to make it like resistant to water penetration, so that if you drop water on it, it won't like go right through. Toilet tissue is not. That's designed. That has fillers in it to absorb paper. This writing paper has stuff in it to try to repel water. All right, but anyway, when you heat this stuff up, the actual fiber structures are still there. They're just a carbon backbone. I won't go through too much of this because it's a little bit. But X-ray diffraction, I just want to get you an idea of what's available here at Miami when you do research. X-ray diffraction allows you to look at crystal structures and materials. And through the library, this peak here is calcium carbonate. If we heat it up to 900, the calcium carbonate goes away. It goes to calcium oxide. This is FTIR. We have these here also. And these two peaks here are indicative of calcium carbonate. And here we have a TGA. This is mass, relative mass versus temperature. So if you put a sample in this little cup, you can see how temperature, how the mass of that sample decreases as you increase the temperature. Anyway, this blue line here is a raw DPS. This is all your cellulose fibers gasifying. And here's your calcium carbonate decomposing. So the question is, does it work for mercury vapors? This is at 30 degrees C, and then this is a comparison at 140 versus 30. What you see here is mercury concentration versus time. What this shows is immediate breakthrough. So it didn't absorb anything at 140 degrees, but at 30 degrees, it has some capacity for mercury, which isn't bad. If I had done my literature review better, I would have known that this result would have happened. In dry nitrogen, which is what this was in, carbon doesn't have much of a absorption capacity for mercury at all. What happens in the flue gas is that coal also contains sulfur and it contains chlorine. And it's the sulfur and chlorine that attach to the carbon and form sites that oxidize the mercury. And so when mercury is captured, it's captured as oxidized mercury. That's what I learned from the literature search after I did the research. So, in a nutshell, though, if I was to expand this research, I would look at the absorption capacity of these carbons and under different atmospheres with acid gases in them, and also water vapor. But the question is, this is a BPL, and remember that has a surface area of 1,100 meters squared per gram. And the fact that the breakthrough happens in these two de-inked paper sludge samples at a much later time, I have to ask why. These are surface area is at 50 meters per gram, and this has a surface area of 1,100. So it's not just surface area. So you have to ask yourself why. I see a lot of you, starting to doze, but this is what people do when they do research. They get data, and if it doesn't make sense to them, they have to ask why. Well, I go back to the pore size distribution, and if you look in here, BPL has very low pore volume in this range, whereas the other two have very high pore volume in that range. So I'm assessing that the pore structure has a lot to do with the mercury capture. And when I look in the literature, this is supported by a couple articles that have been published. So key conclusions, yes, we can make activated carbon from pyrolyzed paper sludge. And yes, it can absorb mercury at 30 C. No, it can absorb it at 140 C, but if we did the same experiment with acid gases and in a more representative atmosphere with flue gas, my hypothesis, my new hypothesis for my new research project is that, yes, it would absorb mercury, but I have no data to prove that. That would be a follow-on research project. This is typically how research projects are developed, is you go into the lab, you try something, you get results, you assess the data, and then you figure out, why did this happen? Okay, we got an answer. Now we have new questions, so let that be the hypothesis for our next research project. Does anyone have any questions?
All right, everybody, thank you very much.